This question deals with the addition of alternating quantities, or vector addition. Typically, we do vector addition using x and y components of each alternating quantity involved. Typically, we will use one of the equations as the reference, and the phase of the rest then will be given with respect to that reference. Here, both equations are given as sine wave equations, which means, of course, alternating quantities. And we have then V1, which does not have any angle inside the brackets here, means it goes through the reference. So then the phase relation of V2 with respect to V1 is that it leads by 60 degrees. And so we can write V1 as a vector or a phasor as 20 angle 0 volts peak. Remember, when it's not RMS, we should specify volts peak, because 20 is definitely the amplitude there. And so we can say that V2 is equal to 10 at an angle of negative 60 degrees, again, volts peak. Now, remember that we are asked to find the instantaneous equation and the RMS value. So we can convert these vectors to RMS before we start, or we can complete the addition using the peak values of 20 and 10 respectively. So here then, we will calculate the RMS values of V1 and V2. So V1 has an RMS value of 0.707 times 20, or 14.14 volts. Likewise, V2 has an RMS value of 0.707 times 10, which gives us 7.07 volts. Now, if we draw a phasor diagram, remember V1 is the reference. Typically, our reference is the positive 0 axis, or the positive x-axis, I suppose we'd say. And so we have V1 with an approximate length of 14.14 volts. We have V2 at an angle of 60 degrees. And V2 then has an approximate length 7.07 volts. To add these, the parallelogram method suggests that we complete the parallelogram method, and the resulting vector is the V resultant we want at some angle theta. Now, the diagram gives us an approximate answer, which we can verify using vector addition. Vector addition tells us that we should find the x component of our resultant by adding the x components of V1 and V2. We should find the y component of our resultant by adding the y components of V1 and V2, and that would give us the reference at the same angle theta. Now, you might find my diagrams are not to scale, but the idea is that if we had drawn them to scale, we should come up with an accurate answer. The reason why we use the vector addition using the x and y components calculated using sines and cosines is that that improves the accuracy that we could get from drawing a sketch, and makes the calculation quite a bit faster as well. And so now what we'll do then is we can make a little table, and the table, let's say that we have Vx and Vy and So that would say that here we have V1, which has a value of 14.14 at an angle of 0. V1x equals 14.14 times the cosine of 0 degrees. And we'll find that the cosine of 0 degrees is 1, so that gives us 14.14 volts. V1y equals 14.14 times the sine of 0 degrees. The sine of 0 degrees, you might note, is 0, and so V1y equals 0. Well, if you remember our phasor diagram up here, V1 points in the x direction. It does not have a y component. And so let us think about V2 equals 7.07 at an angle of negative 60. V2x is equal to 14.14 V1x is 7.07 times the cosine of negative 60 degrees. 7.07 then multiplied by 0.5, and that gives us an x component for V2x at 3.54 volts. Now V2y, 7.07 times the sine of negative 60 degrees, 7.07 multiplied by negative 0.8660 gives us V2y at negative 6.12 volts. Now, the next step is to say that we can produce V resultant. The x component of V resultant will be equal to the x component of V1 plus the x component of V2. And let's call that V2x, we wanted to call that. So we have then the x component of V1, the x component of V2. And so the x component of our resultant will be equal to 14.14 volts plus 3.54 volts. The x component of the resultant is 17.68 volts. Now the y component of our resultant will be V1y plus V2y. And we have 0 for V1y, negative 6.12 for V2y. So have 0 plus negative 6.12 volts. VRY then at negative 6.12 volts. Now, if you refer these back to our original sketch, we'll see that the y component of the resultant below the positive axis, we expect it to be negative. So now, if we go down here and we take these two and we put them on a diagram, we're going to say that the x component of the resultant, 17.68 volts, the y component of the resultant, negative 6.12 volts. And we can use that then to plot our resultant, which then gives us VR at an angle theta. Remember that this is a right angle right here. So Pythagoras' theorem applies to the triangle that we have produced. And so the resultant has a magnitude of 17.68 squared plus 6.12 squared, and we take the square root of that. And we'll find that if you do the math on that, 18.7 volts is the resultant. Now remember that that is an RMS value. It is one of the answers to the question we were asked for the instantaneous equation and the RMS value. So that is indeed the RMS value. The instantaneous equation, of course, includes the angle theta, which will be a negative angle. Now, so in order to produce the instantaneous equation, we would like to say that V resultant is equal to VR maximum or peak value times sine of omega t subtract theta volts. Now we don't know theta, we have the resultant RMS value, and so the peak value of the resultant would be the RMS value over 0.707. 18.7 divided by 0.707 gives us a peak value for the resultant of approximately 26.5 volts. The angle theta given by trig, whereby theta can be calculated as the inverse tangent of the vertical component VRY over the horizontal component VRX. So the inverse tangent of negative 6.12 divided by 17.68 is one of the ways that theta can be calculated. If you do this, you should come up with negative 19.1 degrees. Now typically it is acceptable to put degrees in the instantaneous equation right here, as long as you indicate that it's given in degrees. And so VR then is equal to 26.5 times sine of omega t. Remember, omega in the original instantaneous equation was given as 377. So we have sine of 377 t subtract 19.1 degrees volts, and this is the instantaneous equation that we were asked to produce.